Hey everyone, now that you have done finding the area through integration, you can now learn how to find the volume of a revolution through integration as well. So let's just consider a graph, right? Let's say we have this kind of like a positive side of the EX graph, and we rotate it 2 pi or 360 degrees about the x-axis completely, and we sort of like get this figure. So something like this, sort of like a flask or a vase, right? So how do we then use integration to find the volume of this figure? So we go back to the original idea of integration, right? If you want to find the area underneath this graph from, let's say, this point A to point B, we would take like multiple, we would take an infinite number of rectangles of very small widths, right? And if you add these areas of rectangles together, you'll get back the area underneath the graph, correct? Same thing for volume of revolution. What we can do is we'll keep slicing, okay, to obtain this infinite number of cylinders, right? Because if it's like a Swiss roll, you take a Swiss roll, you cut it, you'll get these smaller size cylinders, right? Pieces of with delta x. Delta x because it's parallel to the x-axis. So what is this going to do? And how do we use this information to find the total volume of this figure? So we'll add these infinite number of cylinders, right? The volume of these cylinders, which will then get us the total volume of revolution of this figure. So to find the volume of one cylinder first, well, it's basically area times the height of the length, right? The height here is delta x. The area is basically the circular area, the circular base. So what is the radius here? We know that the volume is basically pi r square delta x. So what is the radius of this cylinder? If you go back to the original graph, you notice that the radius is simply y, right? Because from the graph itself, so let me use a different ink. So from the graph itself to the x-axis is y, right? This height here is y. And therefore, the radius is y. And we then have the volume of one cylinder being pi y square delta x. Because of an infinite number of cylinders, we will then perform integration, which will then give us pi the integral of y square dx. So this is about the x-axis. The y-axis is actually pretty similar. If you were to rotate the figure about the y-axis, we will get this figure instead. Correct, so we have the same graph. And then now, if we rotate completely about the y-axis, you'll get this sort of like a cone or a bowl, right? Something like this. And you notice, if we were to cut, we're gonna get discs as well, right? Or cylinders as well. This time around, the cylinder is sort of like a tin can when placed correctly. Okay, something like this, okay. So again, what is the width? The width here is delta y, right? Because it is parallel to the vertical axis and you're taking very small width, so it's delta y. What is the radius? X, correct? Because you're taking from the y-axis to the point of each curve, right? So from here to here is x. Therefore, the radius is x. One cylinder, volume of one cylinder, would then give us pi x square delta y. Because it's an infinite number of cylinders, we will perform integration to give us integral of x square dy. All right, so this method is actually called the disk method. So we have the volume of revolution, which is the disk method. Why disk? If you think about the cylinders, right, they look like a disc, right? So that's how the inspiration comes from. So we then have this formula. So if it's rotated about the x-axis, the formula is pi y square dx. If it's about the y-axis, it will be pi x square dy. All right. So how do you actually kind of like memorize this? It's basically the axis that you're rotating about would be the variable that you're integrating with respect to. So if you're rotating about the x-axis, you'll be integrating with respect to x, and then therefore y squared, because y must be a function of x. You can only integrate with respect to x, therefore it will be y squared. Y-axis, if you're rotating about the y-axis, you'll be integrating with respect to y, therefore dy, because you can only integrate y variables, therefore x squared, where x is a function in terms of y. So how do you know when this method is valid, correct? Very simple. If you notice from the example just now, right? If you know that the volume is something like this, right? You're rotating about the x-axis. If you notice that you can get like disk, right? So something like this, you get like disk. You slice across, you get cylinders. You will get the disk method. Similarly, if you have to rotate about the y-axis, you notice that you'll be cutting across like this. You get this as well. You then therefore can use the disk method. However, if let's say you have this graph instead, and you're rotating, sorry, not this graph. Let me think. Let's say you have this graph, and you're trying to find the volume from, let's say, over here, x equals to a to x equals to b, in terms of, and you're rotating about the y-axis, you realize that, wait a minute, I don't have any disk here, right? There's no disk here because this volume here doesn't even cover this area here. So you cannot use the disk method here because this method only works for the x-axis but not for the y-axis. So this cannot be used. You cannot use the disk method for the graph on the right. However, there's another method to find the volume for the graph on the right, which I'll show you in the next video. But regardless, this is one technique that you will learn. It's basically whatever axis that you are rotating the graph with respect to. So let's say you're rotating about x, right? You try to draw the lines towards the axis. If it touches, right, without exceeding the graph, then it would be the disk method. So for in this case, you notice you can just draw it down from the graph to the axis, so it'll be okay. If you're rotating about the y-axis, you notice, hey, it's fine as well, right? So this is the perfect example for the disk method. So yeah, there we have it, the disk method to calculate the volume of revolution.